Hi everyone, we've been talking about how to make denominators nice, whether it's by taking the conjugate of a radical expression or the complex conjugate of an imaginary expression. Let's talk about how complex conjugates help us. Now before, we used to let x represent a real value. Now, more generally, we often represent a complex value by the letter z. So let z be a complex number. That is, let z be in the set C. Then z bar denotes the complex conjugate of z. So if z is written in standard form, a plus bi, where a and b are real numbers, then z bar is a minus bi, where we switch the sign on the imaginary part. So let's take a look at this table. If z is 3 minus 4i, what is the complex conjugate z bar? It's given by 3 plus 4i. And think about how these are related in the complex plane. How are they related? If you graph these two numbers as points in the complex plane, how are they related? Next, how about negative 1 plus 2i? Its complex conjugate is what? It's going to be negative 1 minus 2i. You only switch the sign on the imaginary part, not the real part. Here's a trick question. What's the complex conjugate of 5? Hint, what's the complex conjugate of 5 plus 0i? It's 5 minus 0i, or just 5. Bottom line, the complex conjugate of a real number is just itself. Finally, what's the complex conjugate of negative 4i? Well, here's a hint. What's the complex conjugate of 0 minus 4i? It's 0 plus 4i, or just 4i. By the way, sometimes in some books, when they write out numbers as complex numbers, they sometimes write 5 as 5 plus 0i and negative 4i as 0 minus 4i. I won't require that, but some books go into overkill and they actually do that. It's a very explicit standard form. All right, now again, how are these complex numbers related to their complex conjugates? Well, we get reflections about the real axis, this horizontal axis. So for example, 3 plus 4i goes to 3 minus 4i, and vice versa. Also notice that 5 over here, which is a real number, its complex conjugate is itself. So the numbers on the real axis are fixed points when you consider taking complex conjugates. The complex conjugate of a real number is itself. Okay, so once again, complex conjugates are used to help us make denominators nice. But how do they do that? How do they do that? In addition to the remainder theorem, this is one of the shortest theorems you'll find in pre-calculus. If z is a complex number, then z times its complex conjugate will be a real number. In other words, for any complex number c, zz bar is real. A complex number times its complex conjugate will be a real number. Here's a proof. Let z be of the form a plus bi, where a and b are real. That's standard form. And by the way, in many proofs in 200 level classes, we often start off with something like this. Let z be a plus bi, where a and b are real. Well, what's z times z bar? Its complex conjugate. It's going to be the number a plus bi times the number a minus bi. We're multiplying two complex numbers. Well, how would you multiply the factor a plus b times the factor a minus b old school? Well, remember, this is the factorization of a squared minus b squared. Or do your FOIL trick and know that the cross terms cancel out. But the result here is a squared minus b squared. So likewise, if you're multiplying this sum by this difference, it's the square of the first guy, it's a squared, minus the square of the second guy, the square of bi. Before we didn't have the i's. And we had a squared minus b squared. Now we do have the i's. And we have a squared minus the square of bi. You share the square here, and you get a squared minus b squared I squared. What was I squared? It was -1. Put parentheses here to remember that it's multiplied onto the b squared, or the opposite of b squared, over here. So ultimately, we're going to get what? We are ultimately going to get a squared plus b squared, where a and b are real. Well, the sum of the squares of two real numbers will be a real number. A squared plus b squared will be a real number. So therefore, ZZ bar is in the reals. And ultimately, we'll be able to realize or rationalize denominators. So notice this now. Yes, we've shown that z times z bar is a real value here, but look at this. Look backwards. A squared plus b squared is equivalent to all this back here. The factor a plus bi times the factor a minus bi. This is factoring. So for the first time, we're able to factor, that is, we're able to get a factoring rule for the sum of two squares. We had a factoring rule for the difference of two squares. Here it was, when you look at this in reverse. But now we have a factoring rule for the sum of two squares. We now have a rule for factoring the sum of two squares, which we didn't have before when we kept it real. But now, if we're allowed to use I, we can factor a squared plus b squared like so. And we're going to use this factoring rule a lot. So this set of equivalencies here shows why using complex conjugates is helpful to help us realize denominators, and also it gives us a factoring rule for a squared plus b squared. All right, next up, we're going to show how complex conjugates can help us divide complex numbers.